Okay, we are going to try to finish this 1998 AP Calc BC multiple choice exam in this video. We are on the graphing calculator required portion now. So let's get started. I have not solved these problems before, pre-solved these problems before. I might have done these before in my life, but I have not pre-solved them for this video, so let's see how I do. I did find a website where they did solve this, so let's see if I get matching answers with this website, okay? You can easily Google this website also. All right. Now, 76. For what integer k greater than 1, will both these series converge? Well, we know that, okay, let's start with this one. This one looks like it's either the alternating harmonic series or the harmonic series, so we have to pick our k carefully. If k is an even power, it'll be -1 to some even power, because 2 times, or some even number times some value of n, doesn't matter what that n is, because n is greater than 1, as long as n is greater than 1, it'll be an even number still, okay? So, if this product kn is to some even power, this -1 to that power would become +1. And if it's +1, that's the harmonic series, and that diverges. Okay, so hopefully that made sense. So one more time, we have to choose k such that -1 to whatever the product of kn is not even. Okay, and we know that when k is an even number, no matter what n is, for n greater than 1, it's going to be even. So k cannot be even. So we eliminate those two choices already, the ones that are even. Okay, so once again, if it's odd, then it's the alternating harmonic series, which we know converges. If it's even, it's the regular harmonic series, which diverges. And for this one, this looks like a geometric series, so we know that the common ratio, k/4, in absolute value, has to be less than 1 in order for this geometric series to converge. So that only happens when k is what? Oh, sorry, we can eliminate this one also for this one, because that was even. So it's either 5 or 3. Well, if this has to be true, then k has to be 3. If it's 5, 5/4 is 1.25. 3/4 is 0.75. So the answer is D. Okay, next, this one's quite easy. F is a vector valued function defined by this guy. F double prime is, the reason I said I could immediately tell it's quite easy is because this is f, we just need to find f double prime. This is a vector function, so we just differentiate each component individually. So let me first find f prime. Is this visible on camera? It is, okay. F prime, what's the derivative of the x component? It'll be minus e to minus t. Derivative of cosine is minus sine. Okay, so f double prime would be the derivative of this guy, which is, derivative of this would be e to negative t. Derivative of this would be minus cosine. Okay, so that looks like, which one? This looks like this one, e. Okay, so I get the matching answer, good. All right, this one I did in the AB video. I do recognize this. Let me just redo it. Radius of a circle is decreasing at a constant rate of 0.1 centimeter per second. So I want to jot down dr dt is minus 0.1. In terms of the circumference C, probably want to use that. What is the rate of change of the area of the circle? So that's dA dt in square centimeters per second. So that's just the unit. So we want what dA dt is in terms of C, though. That's what the problem's asking. What is C in terms of the radius, circumference? 2 pi r. What's area in terms of the radius? Area is pi r squared. This is a circle. Okay, so we differentiate the area formula. dA dt is 2 pi r dr dt. We know c is 2 pi r, so we can replace that with the variable c. What's dr dt? They give that to us as -0.1. By the way, I don't know if I said this already. We put it as negative because it's decreasing. Okay, so it's -0.1 times c. Moving on. F is this guy. For what positive values of A is F continuous for all real numbers? Okay, so the brute force way to go about this is, let me just go choice by choice. If A is 1, well, the bottom you would be able to factor as, so I'm just writing the denominator, it'll be x plus 1, x minus 1, okay? So x cannot be -1, nor can it be 1, okay? I don't know if that's visible there, but that's this, okay? Let me write it one more time. X plus 1, x minus 1, like this, okay? So, as I said, this is the denominator, so if x is -1 or 1, that would make this, that would be asymptotes there, or maybe actually even a removable discontinuity, a whole, so that would make it discontinuous, so it cannot be this. Similarly, for 2, it'll be, the solutions would be like square root 2 and negative square root 2 or something like that. So it cannot be this either. If it's 4, it would be, there'll be a whole at x is 2 and -2, it looks like, right? Since it'll be the same as the top, which we can cancel, but that's a removable discontinuity, so not that. 1 and 4, I just argued 4, and not long ago I argued for 1, so we eliminate all those, we're left with none. Okay, so that's how I personally would approach this. Actually, this website that solved this got the same answer, but they did something that doesn't make sense to me at all. Okay, but that's how I would approach this. Just the brute force way. Let R be the region enclosed by the graph, this guy. The x-axis and the line x is -2/3 and x is 2/3. Closest integer approximation of the area R is, so we should just plug this into our calculator. So let me do that right now. Okay, so if I graphed it correctly, it should look something like this. Okay? I had to zoom it like this because if I zoom it out more, it's going to be written in terms of pi, the tick marks, which I don't want. So for this particular case, well, this is always above the x-axis, so it might be a good idea to integrate with respect to x. And they even give us the limits of x, go from -2/3 to 2/3, so minus 0.66 around, minus 0.67 to 0.67. So what is this point over here? Actually, we can even use our calculator to find it, so it'll be find roots. So this is a little bit bigger than -2/3, okay? And similarly, over here would be, it should be a little smaller than -2/3 because 2/3 is 0.667, it's 0.6 repeating. So it's a little bit bigger, okay? So we'll be within the two zeros, okay? So we just put in our calculator the integral -2/3 to 2/3 of 1 plus log cosine of x to the 4th, like this. And I need another parentheses, I believe. Let me write it like this. dx. Okay? By the way, I believe you could pull this 4th power out because it'll be cosine x quantity to 4th like I did this, but properties of logs, you can just pull it out. I believe that should be valid too. Okay? So just plug this into your calculator. It's f int of whatever that is. And let me put it into Wolfram Alpha right now to see what I get. So I put it into Wolfram Alpha, and it looks like it's 0.919, something like that. So the answer looks like it's 1, or choice B. Okay? All right, we have derivative of, with respect to x is this guy, then the second derivative is what? Okay? So we need to implicitly differentiate. Okay? So if we differentiate this side, that's exactly this. If we differentiate this side, it will be 1 over 2 root 1 minus y squared times minus 2y by the chain rule, but then we're implicitly differentiating, so dy dx, the minus there. Okay, so times another dy dx there. Okay, so what happens? Well, we know what dy dx is. It's exactly this. And this dy dx can cancel with whatever's here on the bottom. Okay, so we are left with minus 2y over 2. So that's simply minus y. 81 is B. Okay, 82. F of x is g of x plus 7 for x is between 3 and 5. The integral from 3 to 5, f plus g dx is what? Okay, so we just plug in that f of x is g of x plus 7, I believe. So then we could get integral from 3 to 5, g of x plus 7 plus another g of x by dx. So we can write it as 3 to 5, 2g of x plus 7. Okay, and we can even break up the integral. Let me just go slowly. 3 to 5, 2g of x dx plus integral from 3 to 5, 7 dx. Okay, this we don't know anything about g, so we leave alone, but this we know it is. Okay, so let me rewrite it once more. We can even pull the 2 out, 2g of x dx. This guy would be plus 7 times 5 minus 3. This would be 2. 2 times 7 would be 14. So we should get this as our answer. It should be. Okay. Taylor series for ln x centered at x is 1 is whatever's given there. Let f be the function given by the first sum of the sum of the first 3 non-zero terms in this series. Maximum value of ln x minus f of x in absolute values for x is between 0.3 to 1.7 is what? This is basically what's the maximum error between the Taylor series approximation, Taylor polynomial, and actually ln x. Okay, so let's write out the first 3 non-zero terms of f, the power series, or the Taylor polynomial. Okay, f would be what? We plug it in as 1, we get, it will be negative 1 to the 2 power, so that's positive. We get x minus 1 is the first term over here. Okay, and then second term would be negative squared over 2. Third term would be positive x minus 1 cubed over 3. Okay, so this is the first 3 non-zero terms of the series. Okay, so we can, how should we approach this? We have this interval. We want to, well, actually we can just subtract ln x with what we found here. So put this as, like, put ln x as y1, put f of x as y2, this is what we found, and then y3 is y1 minus y2. I believe that's a valid place since we have a calculator, so let me do that. Okay, so my app on my phone doesn't have that y1, y2 option, so I just put everything in one line, so just ln x minus this. And we're interested in 0.3 to 1.7, so give me one more moment to adjust the scale of this graph. Oh, also don't forget the absolute value. Okay, so I forgot that almost, and let me put that also. So this is how it looks after I graphed it, so you can see that big piece there. So we're interested in 0.3 to 1.7, so 0.3 somewhere here, 1.7 somewhere here. So it looks like we just have to check the endpoints, what the value at f of this graph is at 3, and what the value is at 1.7. So am I able to do that on this phone? I might not be able to. Or I guess this is tracing it. Okay, so when x is 0.3, So a little more. So around here, let's say. I'm sure you can get it more accurate with your calculator. So it's the red says it's 0.145 around there. So 1.7 is 0.04. Okay, so the maximum value is 0.145, we said. Or 1.144, I don't even remember what I said. I just remember it's 0.14 something. So it was C. So that's how we can do this problem, okay? Hopefully that made sense. What are all values of x for which the series converges? So this is just testing interval of convergence. So we could do it the long way. So let me just do that, and then we can go by the choices also. That's, I feel like, the quicker way. But let me just do it the proper way for education purpose. Limit as n goes to infinity. We're doing the ratio test, by the way. That's how we find the radius of convergence, right? So it will be x plus 2 to the n plus 1 over square root of n plus 1 times x plus 2 to the n square root n. Okay? So we get limit as n goes to infinity, x plus 2 remains on top, and then we still have square root n over square root n plus 1. Okay? Limit as n goes to infinity, so this doesn't depend on n, so we can move that out, actually. How about here? Well, remember, there's a very shortcut way where, since you don't know how to show work, we just do a degree test still. We just picked biggest degrees. In this case, it's technically n to the half. There's the same degree on top and the bottom. We take the ratio of the leading coefficient, which is square root 1, which is 1 for both. So the limit would be absolute value x plus 2 times 1, which is just this, right? So we want this to be less than 1 per the ratio test for it to be convergent. So we get x plus 2 has to be less than 1, but greater than negative 1. Or x is less than negative 1, but greater than negative 3. So we have to check our endpoints still, but we could already eliminate some of the choices because we can eliminate these two, actually, okay? So now we have to check the endpoints. What happens when x is negative 3? Well, we would get minus 1 to the n over square root n in the summation. Does this converge? Does this diverge? Well, this looks like an alternating series, so can we use the test? Alternating series test. 1 over square root n is a decreasing series, so we are allowed to use the the alternating series test if the limit of this goes to 0, which it does. So we know that this one converges by the alternating series test. Hopefully that made sense. Hopefully you followed along. How about x's? What's the other limit? Negative 1. We get summation when x is negative 1, we get 1 to the n, which is just 1 over square root n. We know this diverges because this is a p series. P is equal to half, which is not greater than 1. Okay, so it should include negative 3, but not include negative 1. So 84 should be B. Okay, so this is a long way to do it. So since this is a multiple choice, you could just go by the choices, actually. You can plug in the endpoints from here, actually. So we can, for example, if we start from choice A, we plug in x is negative 3, so we just do this portion, what we did here. We know that that converges, okay? And we found that x is 1, because this is the other limit, right? Diverges, okay? So actually, first of all, let's back up. If we first plug in x is negative 3, and we found it to be convergent, which we did, it must include negative 3, the interval of convergence. These two don't include negative 3, so we still cross them out, okay? And then we would be able to cross this out also because it does not include negative 3. So it's one of these two, and then we do the other points. X is negative 1. We find that it's divergent, so we hone in on B. We can eliminate C also. So that's the quick way to do these types of problems. You could possibly go by the choices and determine it from there. And of course, if you do have extra time, just do it the long way to double check. At least for the the interval, and then the endpoints you would have already done actually. But yeah, hopefully that makes sense. Okay, function f is continuous on the closed interval 2 to 8 and has values that are given in the table above. Okay, so I think I did this into not 2a, the AB problem sets, AB test. So I'll just do it again though. The key thing here is we're doing a trapezoidal approximation, but you have to pay attention that these are not equal intervals. This is the length of 3, this is the length of 2, this is the length of 1. So you got to be careful. You can't use that general trapezoid approximation rule that you might have learned. So you got to actually add up the different trapezoids here, okay? So how do we do that? Well, area of a trapezoid is average of the bases times the height. The height is delta x. So it'll be, in this first interval, it'll be f of 2 plus f of 5, which is 10 plus 30. You take the average, so divide by 2, times delta x, which is 3, plus we get the next interval, 30 plus 40 over 2 times 2, plus 40 plus 20 over 2 times 1. So this is what? This is 40 divided by 2, that's 20, times 3, that's 60, 70 divided by 2, well, this times 2, and divide by 2 and times 2 cancel, so we have 70 here, and then here we get 60, so it is it 190? I forget. It's not, because here I made an error, it's plus 30 there, sorry, because this will be 60 divided by 2, which is 30, okay? So this is 160. Okay. This one I'm pretty sure I did in the AB video also. Let me do it again. Base of a solid is the region in the first quadrant bounded by x-axis, y-axis, line in the sky, as shown in the figure above. If cross sections of the solid perpendicular to the x-axis, so this is signal, we're going to integrate in terms of x, dx, are semicircles, what is the volume of the solid? So you can imagine, well, let me draw it without the shade over there. Cross section perpendicular to the x-axis are semicircles, so we have a semicircle here, we have another semicircle there, it looks something like that. Each semicircle has a width of dx. Hopefully this sounds familiar. Okay, so how do we get the volume? Well, how do we get the area of the semicircle? It should be half pi some radius squared. Notice, this is the diameter. So what is this length of this diameter? It's this guy, the function. Or let me solve it in terms of y. It'll be y is 8 minus x over 2. Okay? This length is 8 minus x over 2. So we divide that by 2 again to get the radius. So it'll be half, well, let me just do 1/4 pi, actually no, we can't do a fourth blindly because it's r squared. So we got to go like this. Half pi 8 minus x over 2, divide by another 2, so over 4 squared. Okay? And then it's actually like this. Okay? So one more time. We want to find the volume of the solid whose cross sections perpendicular to the x-axis are semicircles. So each cross section, the volume is the area of the semicircle times a small width dx. So let's find the area of the semicircle. It's half pi r squared. What is r? Well, the diameter is here. Diameter is this guy, 8 minus x over 2. So we half that to get the radius. So it'll be 8 minus x over 4, okay? And then it has that small width dx, and we just integrate. What are the limits of integration? We integrate it in terms of x. So it's from 0 to 8. Let me plug this into my calculator to see if I got this right. So I put it into Wolfram Alpha, not into my graphing calculator app, but I got 16.755. So then that is C. Okay, that's how we set this up. So I think probably the common mistake is this, notice, is the diameter, not the radius. So you got to be careful for there. Which of the following is an equation of the line tangent to the graph of this guy at the point where f prime of x is equal to 1? Okay, so interestingly, they give us the slope. We need to find the point now. Usually they give us part of the point and we need to find the slope. Something like that, right? This is now a little bit different, but everything should be straightforward. So if you recognize this, okay? So they give us the slope of the tangent line is 1. So where does that occur? So let's find f prime. That is 4x cubed plus 4x. We set it equal to 1 because that's what we want. Okay? So we can factor out, actually let's not factor, let's just, what should I factor? Well, we shouldn't factor, rather we should move the 1 to the other side to solve for x. Because that's how we solve for x. And, well, actually, this you can't factor, I think. So you need a calculator, actually. So wouldn't have mattered. So you could either set this equal to 0, find the roots, or you could set this as one line, y is 1 as another line, find the intersection. That's totally valid also. So let me put this in my calculator. Give me one moment. Okay, so this is the graph I got. And the solution to this guy is x is 0.2367. Okay, so when x is 0.2367, what is y equal to? We just plug x is 0.2367 into f here. So what would that be? Let me, 0.2367. That is this guy to the 4th power plus 2, that guy squared. So y should be like 0.11519, something like that. Okay, so we have a slope, we have a point now, so we can use point slope form. y minus 0.115, let's round, is equal to 1 times x minus 0.237. Let's just round. It should be okay since we'll get something close enough probably. So we got y is x minus 0.237 plus 0.115. So let me put that into calculator, minus 0.237 plus 0.115. So it should be minus 0.2122, this one. Okay, so that's how we solve this one. Let g, I think I did this in the AB video, g be integral from a to x f of d dt, where x is between a and b. The figure above shows the graph of g on interval a to b. Which of the following could be the graph of f on the interval from a to b? So if this is g, then when you see something like this, you probably want to take the derivative so that we can apply the fundamental theorem of calculus. So g prime is actually just f of x by the fundamental theorem of calculus. So this helps us right away. If this is g, what is g prime? Well, since it increases up to this max, so the derivative should go from positive to negative somewhere in the middle of the interval, okay? So it should, the derivative should, so the slope of the tangent line is the derivative, right? So it should get more steep, and then it gets less steep, and then it falls off afterwards. So let's see. Well, we know that this derivative changes sign twice. There's only one relative extrema in this interval. We don't know what happens at b, but after b, but so it cannot be a. As we said, at this point, the derivative should go from positive to negative, which this one does not. This one does. This one does not. This one does not. So we're left with choice C. Okay. Okay, we are approaching half an hour. How many more problems do I have? I think 3 more. Let's finish this. 4 more, okay. Let's see. Graph of the function represented by the Maclaurin series, the sky intersects the graph of y is x cubed at x is equal to what? So this is probably a series that you should know or very close to it. And actually, I can tell right away that, well, it looks very close to e to the x, but there's some differences in the sign. So maybe it's like e to negative x, okay? Because we know how e to x is. This is 1 plus x squared over, 1 plus x squared over 2 factorial plus x cubed over 3 factorial, so on and so forth. So when it's e to the negative x, I would cut off, e to the negative x, it'll be 1 minus x plus x squared over 2 factorial minus x cubed over 3 factorial, so on and so forth, which looks like this, okay? And yeah, this is exactly it, okay? And you can even look at this term if you recognize that e to x is x to n of n factorial. We have this alternating sign though, so then that came from this e to negative x, okay? This negative x. So this is e to negative x. We want to see where it intersects y cubed. So this is a calculator question again, so let me quickly put that in my calculator. So we have e to the negative x, and we have x cubed. So how do the graphs look? This is what I immediately get. We want to see where they intersect. What's the x value? That is 0.772. So it looks like A. Okay. Particle starts from rest at the point 2, 0 and moves along the x-axis with a constant positive acceleration. This is probably key. For t greater than or equal to 0. Which the following could be the graph of the distance of the particle from the origin as a function of time. Okay, so if you know like physics, kinematics, this should be very easy. We know if there's a constant acceleration, then the position should be quadratic. Okay, if you don't know that, that's okay. When we start from the point 0, 2, that you can already eliminate a lot of them actually. Because what Mr. Following could be the graph of the distance from the origin. Well, at rest, what's the distance from the origin? It should be 2. So there should already be a starting point of 2 for the graph. So we can eliminate this one, so these two, okay? It says constant positive acceleration. This guy, position S, or the distance from the origin, is not moving. The distance is not changing. There's no acceleration. This one is constantly moving at a certain rate. The rate, or the derivative, is constant. So once again, there's no acceleration then. So it has to be A. Okay, hopefully that made sense. And if you know physics, kinematics, all that, we know the general formula for that position is like if it's x of t is x0 plus v0t plus half constant acceleration a t squared. So we know that the sky should be quadratic. So that one was quadratic and started at 2. This one's quadratic, but it didn't start there, right? So we can eliminate a lot of the choices if we just knew this. But you didn't have to know that. But just knowing physics in this particular scenario would have helped. Okay? All right, let's speed up 2 more problems. Okay. Data for the acceleration of a car from 0 to 6 are given in the table above. If the velocity at t equals 0 is 11 feet per second, approximate value of the velocity at t equals 6, computed using a left-hand Riemann sum with 3 subintervals of equal length is, okay, so when it says Riemann sum, that immediately should tell you we need to integrate, okay, and even says left-hand Riemann sum, okay, and we're just approximating the integral with rectangles. That's what that Riemann sum is, remember? Okay, so this is the acceleration. We want to find what the acceleration is at t is 6. So we need to integrate this guy and add on this initial velocity of 11, okay? So we can't forget that after we integrate. So let's integrate with a left-hand Riemann sum. So that would be, so this first interval, so by the way, it says 3 equal subintervals. Yeah, 3 subintervals of equal length, t from 0 to 6. So conveniently, they already give it to us here. But if we didn't know, remember the delta x formula is 6 minus 0 over 3, which is 2. So the delta x should be 2, or delta t in this case. Let me write that. Delta t should be 2, which it is. They do give it to us as 2. So we can factor out that delta t. So 2 times. So we take the left endpoints. So it would be 5 plus 2 plus 8. Okay? Because it'll be a rectangle of height 5 with width 2. So 5 times 2. Next rectangle would be, again, a width of 2. Height is 2. We're taking the left endpoint. And last, the width of that rectangle is, again, 2. The height is the left point, which is 8. So it should be, what is this? This is 15 times 2 is 30. But remember, we're not done yet. So don't get fooled by this one. We need to add on this initial velocity of 11. So it should be 30 plus 11, which is 41. Okay? All right, let f be the function given by this guy. Line tangent to the graph of f at x is equal to 2 is used to approximate values of f of x. Okay, so this is probably a linear approximation. Which of the following is the greatest value of x for which the error resulting from this tangent line approximation is less than 0.5? Okay, so when in doubt, you should take a derivative because it even talks about tangent lines. So maybe let's take the derivative first and see how we can use it. Okay, f prime is what? 2x minus 2. Okay, so now what do we do? Line tangent to graph of f at x is equal to 2 is used to approximate values of x. Okay, so, okay, I think I kind of see the picture now. So let's find the equation of that tangent line at x is 2 first. Okay, so we evaluate f prime at x is equal to 2. I'm not sure if I'm doing this, if I'm doing unnecessary things, but this is how I'm thinking through it, okay? I didn't look at the key. I don't even know what the answer is. Okay, so when we do that, we get 4 minus 2, which is 2. So slope of the tangent line at x is 2 is 2. If x is 2, what's the y coordinate? It'll be 4 minus 4 plus 3, so y is equal to 3 in that case, okay? So we have a slope, we have a point. Let's find that tangent line. Y minus 3 is 2 times x minus 2, okay? So let's even write it like this, okay? I don't think we need to simplify because we need to put it in the calculator anyway. Okay, so this is the tangent line approximation. Okay, so we want to use this to approximate values of f. So remember the tangent line, this is exactly the linear approximation. So if we have this point and we draw the tangent line, for very nearby points, as you can even see, that it's a pretty good approximation. The area is quite small. But as you get further from the points, you see the error increases, right? Well, that's the idea. So we can just take the difference of this guy and this guy, is what I'm thinking, and see what the biggest value of x is, or see where that, so, okay. So let's call this y2, and let's call this y1, okay? So the error, let's call y3, this is the error, would be what? y1 minus y2. Okay. I'm just confused if it should be y2 minus y1, y1 minus y2. I guess we could just put absolute value, and that should be okay too. Okay, so let me graph this and see what happens. Okay, well, so let's hope I did this right. So this parabola looking like thing is exactly what I described here. We took the absolute value of the original function minus our linear approximation. Okay, so that's, you can even see that there, that huge line. And then I set y2 as 0.5 because we want to find where the point is such that the error is less than 0.5. So that's this point it looks like. Let's find the intersection. That is when x is 2.7 per our calculator. Is that the answer? That is. Good. Okay, so that's how I would approach this. So let me recap one more time. We are going long, but let me just recap. We found the equation of the tangent line that's here. Why did we want to do that? Well, first of all, I even said tangent line and all that, so it was a good idea to probably find it. But remember the tangent line is the same thing as the linear approximation formula, which I never remember because it's exactly the same thing, as I just said. So, and remember why we make linear approximations using a tangent line? Well, for nearby points, you can see the error is small. Okay, so it's a pretty good approximation. So this is saying that if we use the tangent line to make an approximation to f, by the way, I just sketched a random function. This is not f and this is not this guy, okay? What did I say? So if we use the tangent line to approximate f, for what value of x will the error be 0.5? Like, what's the cutoff that the error is less than 0.5? Okay, because any bigger value of x, any further away, then the error will get bigger, I guess. Okay, so that's what this is asking. So we found our tangent line, so we just subtract it from the original function, and I absolutely value it because doesn't matter if the error is negative or if it's smaller or bigger. I just care that the error is less than 0.5. Meaning that it makes sense. Sometimes if it's an overestimate, there we go. That's the word I'm thinking. Then the error would be on one side. If it's an underestimate, the error would be on the other side of the x-axis. Okay, something like that. So that's why I put the absolute value sign, because I don't care if it's overestimate or underestimate. I just care that the absolute value of the error is less than 0.5. So that was this guy over here. And then I found that point, because this point would work, but that's not the biggest value, because these values over here, remember I said it's for close by points. Whoops. So it makes sense that it looks like that. So what was I saying? So we picked this point because this is the bigger x, and that was the point 2.7. Okay. Hopefully that was helpful. This one was definitely more involved with the calculator, but that's okay. This is a more recent exam also, 1998. So it should be more representative of BC calculus also. Okay. Please give this video a like if you found it helpful, and please don't forget also to subscribe to the channel.